Hello friends, in this video we are going to talk about a question from Winter 18, paper 42, and you can see this is a, looks like a current balance, right? Okay, so let's start with part A first, which is a basic warm-up question. You're asked to define magnetic flux density, and normally the definition for magnetic flux density, otherwise symbol is B, has 3 marks. Alright, so a lot of points you need to cover in your definition. So since this is a wire, I'm going to define B using straight conductor. So the magnetic force is equal to BIL sine theta. Okay, so B will be equal to F over L. So force per unit length. And then you will multiply by I. No, wait, divide by I. Sine theta. But we are going to let everything here, the whole I sine theta, be equal to 1. Okay, and we're letting it equal to 1 so that it's easier to define. It's just generally what physics does lah. We let things that are not important be equal to 0. Okay, okay, so this I sine theta, this whole thing, I is 1, sine theta is 1. Or in other words, theta is 90 degree. Okay, so we can start now. If this whole green color bracket is 1, you can say B is equal to F over L. So that will be the first part of the definition. B is the force per unit length. Force per unit length of a straight conductor. Okay, time to talk about the conditions. So this straight conductor is carrying 1 amps of current. So straight conductor carrying 1 ampere of current placed at right angles or placed normal to the magnetic field. Okay, so 1 mark is when you mention is force per unit length. Second mark, you say that there's a straight conductor carrying 1 ampere of current, which is the first condition. And the second condition, it is the positioning of the wire. So this straight conductor is placed at right angles to the magnetic field. This would be the third mark. All right, so this is a definition. We're going to move on to look at the question. Here we have a stiff copper wire balanced horizontally on a pivot, shown in this figure. So of course, the reason why it is balanced is because there's 0 net torque. Okay, so whatever weight of the wire that is pulling it in this direction, counterclockwise, will be the same as the weight of the wire that's pulling it in this direction, clockwise. So they kind of balance out. All right, but let's read the question. Sections PQ. Okay, so where is PQ, QR, and SR? That will be here. So let's highlight those sections. PQ, QR, and SR. So this section here. Is situated in a uniform magnetic field. All right, so the uniform magnetic field is this region now. Ding, ding, ding. Okay, between the poles of the magnet. Now this setup cannot be foreign to you anymore by this point. So there's a magnetic field and there are 2 poles. You don't know which one is north, which one is south. You just know that there are 2 poles here. Okay. Very nice. When the current of 2.7 ampere is passed through the wire, so you got this current, a small mass of 45 milligram, maybe it's a hair lah, okay, or a thread from your clothing, is placed a distance 8.8 cm from the pivot, okay, in order to restore the balance of the wire. So I guess right now, explain why when the current is switched on, the current in the sections P, Q, and RS of the wire does not affect the balance of the wire. Well, I guess when you turn on this current, or let's say this is your 2.7 ampere, and your current is going this way. Ding, 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 go up. All right. So if you want the current to act on the wire, you know, your F is equal to BIL. I mean, sure, you can put sine theta. But the condition here is B and I is never parallel. So if I want to draw the direction of magnetic field, I mean, don't really care lah. You don't draw the direction of magnetic field. Maybe magnetic field is in this direction. This is B. I will just draw one. Okay. So if this is the direction of magnetic field and you want to consider the forces acting on this thing, you will notice that I will take out your FBI law. So once again, I'm going to direct this to a top view on my handy projector. And I will show you how to use your left hand in this scenario where you have 3 different sections of the wire instead of just a single wire in between the poles of the magnet. Right, so you can see I have drawn out the wire on this beautiful piece of paper, and the magnetic field is as usual shaded in blue, right? So you can see that I've labeled this as north and south. So if it's a normal class, I would actually ask you to suggest the direction of the magnetic field to show you that it doesn't really matter whether it's north pole, south pole, or south pole, north pole. Okay, so I guess the reason of showing you this diagram on this piece of paper is for you to determine the direction of forces on the side of PQ, right, QR, and SR. So I want to find the forces on all these 4 sides. You can see that I have drawn the direction of current. So let's start with the one that is closest to my right, which is the side SR. So once again, I'm going to do my FBI, right? So I point B in this direction, so easier for my finger. If you want to be a bit of a rebel and point B in this direction, I guess you can, but then it's not going to look nice. So I just said that lah. Easy on my old joints. Okay, so B is in this direction. Now, where is current? Current is pointing downwards. So your middle finger, B is pointing in this direction. Your middle finger should be pointing downwards. So it's time to rotate your hand to point downwards. B is still pointing in this direction, pointing finger. Middle finger now, okay, let me make sure you can see in the camera, is now pointing downwards. So where is my thumb? So you also should take your hand and try lah. Okay, try together with me. B pointing inwards, middle finger pointing downwards. So stare at your thumb. Where is your thumb now? Pointing in this direction. Middle finger downwards, B towards away from you. Middle finger, thumb will be pointing to the right. So meaning the direction of force for this one. Again, this is a 3D drawing lah, so it's not going to be like super accurate, but I think this is good enough. So this is the force on the side RS. And of course, it's not going to affect the balance because on the other side, if let's say you repeat this Fleming's left-hand rule, but on the side PQ, so B doesn't change, right? Just now, your hand was like this, your middle finger pointing downwards. Now, I need you to keep the same direction of B because we didn't change the pole of the magnet, and flip your middle finger to point upwards towards the camera. 1, are you ready? Put your hand like that. Are you ready? 1, 2, 3, flip. So now your B is still correct. Your middle finger is pointing out. Okay, and where is your thumb? Your thumb will be pointed towards that direction. See my thumb? Pointed towards that direction. So meaning the direction of force on the side PQ will be here. So this is magnetic force PQ. Dun, dun. Okay, I move my hand away. This is not an action-reaction pair, okay? They're acting on the same wire. It's just, you can see that it will cancel off. So even if, let's say, there's a wire here, with this force, right, it wouldn't accept or upset the balance because this current balance, if you imagine, can we put green? Imagine this current balance and the pivot is here. the only way to upset this balance, to tilt this way, or to tilt this way or this way, is to apply a force in this downward direction. So this is your pivot. If you want to tilt this way, you need to press down. Pivot is here. You want to tilt this way, you have to pull down. So the only way for you to pull down is actually the side QR. Okay, so to explain the first part, these two sections will not affect the balance of the wire. All right, that is because they are equal in magnitude. Okay, and they have no net torque about the pivot. All right, we'll write that down. But just for our own satisfaction, I will find the direction of force at the side QR. So once again, pointing finger ready to follow the direction of B. Middle finger will point in the direction of QR. So you will notice that the middle finger is in the opposite direction. So you make sure your B is in the same direction. Keep your B, hold it tight, rotate your middle finger such that it is pointed towards the same direction as the wire. You will find that your thumb is pointing downwards. Okay, so do it together with me. B is pointing inwards. Middle finger. B is pointing inwards. Middle finger, try to follow this direction of arrow. So you turn this way. Now where is your thumb? Thumb will be pointing downwards away. A bit hard to see because my palm is blocking. But my thumb is pointing downwards. So the direction of force on the side QR is actually the one that is pulling this down. So this is FQR. So if you want to find the torque due to FQR, you will take the distance of this force, which is here. Again, this is a 3D drawing, so it's going to look a bit weird. So this distance from here to the pivot, let's say I draw from here to here, is 7.5 cm. All right, the same 7.5 cm. So this force, this torque that causes the system to rotate in this direction will counterbalance with the torque that is produced by the small mass here. So we'll let that small mass have a torque because it has weight, right? So the small mass torque, you can draw on your diagram if you have a diagram. So this one is the mg of this small mass. So to find mg, we will multiply by, once again, the perpendicular distance from mg to the pivot law. So here to here. Okay, which is your 8.8 cm. So FQR times 7.5 is equal to 8.8 times mg. So that way the torque will balance because this mg want to turn it this way. So this moment and this moment kind of cancel out. All right, so don't worry, I'll transfer this one into the drawing inside OneNote. But the whole main idea of showing you this perspective is such that if I move my hand, you can move along with me. Okay, so imagine this is your top view, right? Your top view. B is here. So there are many ways to align your middle finger, pointing up lah, pointing down lah, pointing from right to left lah, Q to R lah. So you adjust lah accordingly and see where your thumb is. Wherever your thumb is, whether it's downwards to this side or to this side, will show you the direction of force. So please practice. I quite like this example because you can actually learn to use your Fleming's left-hand rule in 3 ways. All right, so now we're going to jump back to the calculation and write our explanation on why the force on PQ and RS will not affect the balance, and using our understanding of torque or moment of force to calculate the value of B, which is the part, which is what is needed on the question. So let's go. Okay, so we have looked at the drawing on the 3D first-person perspective. Hopefully that is helpful. Please practice using your left hand to decide the direction of F. Okay, let's look at part B. Explain why, when the current is switched on, the current in PQ and RS does not affect the balance. So if you remember from the diagram I've drawn on the paper just now, the force on SR is in this direction. And the force on PQ using your Fleming's hand is in this direction. All right. So it doesn't affect the balance of the wire because number one, they are horizontal, which means they are parallel to the pivot. So if you apply a force parallel to the pivot, then there's no net torque. All right. It's a bit like, if you draw top view, this is your pivot. Then you apply force in this direction. There is no net torque. Okay. Or I guess another way you could look at it is that they create no moment. No? All right. So that will be the first point. You could say that the forces on PQ and RS, okay, are horizontal. So there is no moment about the pivot. And even if there is, furthermore, okay, the forces on PQ and RS are equal in magnitude and opposite in direction. Not Newton's third law, it's just the way the wire is being wound. So an opposite in direction. Okay, so there is no net force on both sections. So there are two ways to explain, whichever way works for you, easier for you to brain. So the first one, the mark is that forces PQ are horizontal. This is the first mark. This is the first mark here. And the second mark would be no moment about the point. One mark here. Or if you write the purple way, you could say this one are equal in magnitude, opposite in direction. So no net force is the second mark. Okay, so whenever you see certain things doesn't affect the balance or the equilibrium, it's either because there are certain things cancelling out, equal magnitude, opposite in direction, or there is just no net torque. Okay, part 2. Calculate the section QR. The length of QR is 1.2, sorry. Calculate the magnetic flux density B. So if you remember the equation that I've quoted just now, magnetic force is equal to BIL. Okay, so I guess if you want to, you can put sine theta. And then now I stare at the picture. And then where is this magnetic force? Let's say this is FB. This FB is the magnetic force that is acting on the section QR. So the FB, as drawn in the diagram just now, in the piece of paper, this FB is pointing downwards, which causes this entire frame to rotate this way. Okay? And you have this small mass here. This small mass it has a force in this direction, mg, causing this thing to rotate this way. So for mg, since the pivot is here, we will take 8.8. So clockwise moment, mg times 8.8 cm must be equal to counterclockwise moment, which is fb. Okay, so if you extrapolate fb, you will reach here. So fb times 7.5 cm. So cm left right will cancel out lah. All right, so I'm going to transfer this down here. But since it's 3 marks and it's paper 4, I'm a good physics student, so I will write out the explanation. So I could say the sum of the clockwise moment is equal to the sum of the counterclockwise. Miss this one AS1. Yeah, no, but still have to learn ma. So clockwise is due to mg, which is 8.8 cm from the pivot. Counterclockwise is magnetic force times 7.5. 7.5 Is it 7.5? Forgot now. 7.5 cm from the pivot. Okay, so I guess we can now substitute values. So let us go value hunting a bit. Just a side note or a reminder, this is BIL sine theta times 7.5 mg 8.8. Okay, let's go hunt. This is L. I write big L. Okay. Do we have the value of current? Yes, this is I. Do we have the value of mass? Yes, this is M. Okay, what else are we missing? We are looking for the length QR, so this one we can keep it as an unknown. But I think that's it for now. So we substitute lor. 45 milligram. So this will be 45 times 10 to the power negative 3. 9.81. 8.8. If you're wondering why the 8.8 no need to convert, it's because 8.8 is cm. 7.5 also cm. The cm and cm will cancel off lor. Okay, and this will be equal to, we are looking for B, right? So I keep the B here, okay? Divided by I was 7.2, 7.5, 2.7, sorry. So I is 2.7. Okay. L is the length, which is 1.2 cm. Means this one need to convert, of course, because nothing else is going to cancel with this cm. Okay, so we have I, we have L. What about sine theta? What angle to take? Sometimes students tell me, Miss, if they never say then the angle can assume 90. Let's confirm first. Let's go back to the diagram and see. Is it indeed 90? Okay, so if this view is challenging to you, you could draw a top view. I'm just going to write here. Top view. So from the top view, right, what you see is there's this magnet. There's this magnet. Okay. Now, of course, the actual direction we don't know. We can guess only. So this is N, this is S. But you look at QR, right? QR will be here. QR will be placed here from the top view, parallel to the sides of the magnet. Of course, P, the current is going out, so you can use a dot here to represent the current. And at point R, the current is going in, so you can use a cross if you want to be accurate. This is P, this is R. And your direction of current is pointing or flowing from, sorry, not PR, QR, code. Your direction of current is flowing from R to Q. Okay, so I'm putting my eye here. I draw the eye for you lah. And I'm looking down. So what I will see is the top of this magnet, this is north. And top of this magnet, this is south. Okay, and I will see I won't be able to see the frame of the wire. What I will see is I will see the wire QR. So just to see the wire QR is translated here. Current going in on this side, if you want to be very accurate. All right. So direction of current is from R to Q, like so. This is I. So if you use your FBI, you will notice that this one, the direction of magnetic field is here. North pole to south pole. So B and I is already 90 degrees. And if you use your Fleming's left hand all over again, so I'm going to use it there, but the mirror is flipped. So I should use this hand, which will be very confusing to me. But if you use your Fleming's hand, you will notice that your force is going into the paper. Okay, so try it out and see. Align your pointer finger to this B. Okay, then align your middle finger to the I. Your thumb should be pointing inside the paper. That's why your FB is going down. FB is going in. Okay, so this drawing is from the top. Green color is for current. Blue color is for magnetic field. And if you want to draw FB is actually into the paper lah. So I'm just going to draw another cross here for FB. Okay, this is the top view lah. Not so sexy as this one. Okay, but the whole point here of drawing this for you is to show you that B and I is 90 degrees. Which means if we go back to our calculation, your sine theta is 90 degrees. So for this topic, right, visualizing is very important, or learning to draw all the plane diagrams, like what I did, especially if you have problem visualizing. So I'm going to put this in my calculator now. Okay, so the angle, as mentioned just now, will be 90. Don't forget that. And don't forget the 7.5 you bring over to divide. Alright, so I'm a bit squeezed for space, but you write on your paper lah. This one will be equal to B. So I bring everything over one side to divide. Okay, Second thing, I don't know whether you caught this or not, but I should correct this now. This is from milli, but your value for mass should be in kg. Okay, so I'm going to change this to red just as a warning for those of us that may forget. Must times 10 to the power of 3 2 times because m is in kg and the small mass is 45 milligram. So milligram need to change to gram, then only change to kg. So every time you change, you times 10 to the power of negative 3. When you change milli to gram, divide by 1000 ma. Then you times 10 to the power negative 3 again when you change from gram to kilogram. Okay, so you press your good friend Casio the calculator, and that will give me 0.015986666666. Okay, never mind. So this is 0.01599. I guess you could write it into 2SF, so 0.016 Tesla. But of course, if you want to write it in a standard form, you can. This will be 1.6 times 10 to the power negative 2. Okay, just double check the unit so that it's not milli Tesla or any weird Tesla. Tesla the car. Okay, so 1.6 times 10 to the power 2 Tesla. Negative 2 Tesla. Alright, so in this question, the important thing here is when this came out in winter 18, it was a novel situation. Novel situation, novel, N-O-V-E-L, not storybook the novel, but new situation. So meaning this was never asked in past years before, or especially recent past years. So when you're given a novel or a new situation like this, you should know how to use your Fleming's left hand. I know those are my right hand now, but the thing is flipped. So you use your Fleming's left hand to decide the direction of forces. So in this entire video series, we recorded a lot of first-person view, meaning I suspend the camera at eye level and I do the Fleming magic underneath the camera so that you are looking at it from first-person perspective. Please do along with us. Okay, so then you need to think about what forces can do. For example, forces can accelerate something, and of course, forces also can provide some form of equilibrium. All right, so let's say for example I have randomly I got a magnet bar and I don't know how strong this magnet field is. So what will I do? I just fashion some balance like this, like the Chinese traditional medicine shop, and I'll hang some small mass here until this two is balanced, or I adjust the distance of the small mass. Okay, the known mass lah. All right, so then you can use clockwise is equal to anti-clockwise. So the first skill you need to know is don't panic, and remember we are putting current inside magnetic field, so there must be a magnetic force. Use your left hand as a shortcut to quickly find the direction of force. Try to follow the question. Okay, second thing, decide what is happening here. Balance ma, so surely got some torque situation happening. All right, and the small details, like for example because this question gives you a lot of information, so I will choose to circle all these values lah. Like for example, this milligram should be converted to kg. All right, and if you're not sure whether units needs to be converted to SI, you just convert everything to SI lah. Okay, so this is the question. Hopefully you find it helpful. If you are struggling with angles, always draw the diagram either from the front or the top. Draw 2D, it's easier for you to see angle. But yes, as usual, if you find this helpful, please like, subscribe, share our videos with your friends so that we can all learn physics together better. Good luck in your studies, and I will see you in the next one, whatever that next one is that you choose to watch. Bye-bye.